Bienvenuti tout le monde, benvenuti a tutti, welcome everybody. My name is Daniele Pagliero and I'm a musician and the developer of Faselunare, a company based in Turin that deals with the design and construction of electronic musical instruments. Faselunare is run by Alessandro Comanzo, that is the main hardware designer, and Francesco Mulassano, the synth guy that knows everything about synths and is also the organizer of Summit, the most important synth fair in Italy. The purpose of this webinar is to introduce you to Microcosmos, a project started in 2019 by Francesco and Alessandro, and since April involves me as the main developer of the firmware. First of all, what is Microcosmos? It is a small board with a bunch of encoders, buttons, LEDs, and a display with audio and MIDI capabilities that can be programmed over USB by a computer. And what is it for? Making music, of course, but it also aimed to let people prototype and develop their own DSP devices. That's why the code behind of the board is open, and we adopted the Teensy board to create a compact audio laboratory for learning coding and developing ideas in a reasonably easy way, also for newbie or for people into electronics with a small background of programming. Let's see the hardware features of the board. The processor is a Teensy 4.1. It features a color display with software brightness control. We use the latest generation drivers on I2C bus to control LEDs, encoders and buttons. Audio codec works at 24 bits 96 kHz, and there are stereo I/O headphone and an onboard microphone. There is also an USBHost, so you can plug in external controller, and of course there are MIDI in and MIDI out ports. The version you are seeing here is the latest revision and the development is in progress, because we did a great update on the hardware side. To show you the features of the board in this presentation, I will use the first version, different in terms of hardware, but shares the same firmware concepts. The Microcosmos firmware is developed with the aim to let people program the user interaction with the board and to easily change the audio DSP parts. As we adopt the Teensy board, the software can be written and loaded on the board by the Teensy Duino, a software add-on for the Arduino platform. The code is written in C++ language and structured in several folders to make it more readable and maintainable. Here is the overview of the project folder. Later we will see the relevant components in details. Microcosmos.ino is the main entry point. Microcosmos config is the configuration of the Microcosmos params. Then we have defines for various definitions like pin assignment, etc. Then there is the source folder that contains the core classes, that is program and program switcher, Faust, where to place the Faust code, I/O for MIDI in and out, and then programs that contains the logic of the board, and then the UI for control display, buttons, LEDs, etc. Utils for several utilities like converters, math, timers, etc. And then there is the engine, the main engine of the board. Let's take a look on how the Microcosmos is built. The firmware is written around a singleton pattern to develop the main brain of the board, in a way similar to a game engine. This part is called the engine. The engine is the handler of the hardware and software interaction. For instance, it gathers information from encoders and buttons. It updates the display, switches on and off LEDs, and handles the I/O ports, like MIDI and USB. In addition to the engine, and to split low-level functionalities from the logic of the unit, there are programs. A program runs controls by the engine and executes the logic of the board. For instance, it can draw a string on the display, get the encoder value and execute some logic. Then there is the audio DSP part, that is parallel to the engine and can be handled by the program, and it is an export of a Faust script for the Teensy platform. The main.ino initializes the engine, then on the setup part initializes the engine and the programs could be more than one, and pushes them to the list of engine programs. On the loop stage, it recalls the engine loop function. Now, the loop part of the engine does the dirty work, that could be summarized in 3 steps. The first one is reset hardware state, then it executes the current program, and then update hardware. Without going too deep, those operations run a specific frame rate. But there is also a part that is not constrained to this frame rate, and which is faster to cover special needs. The engine also has a way to send messages when something happens. By design, we have decided to use an event-based model, rather than checking the state of the hardware on every loop's execution. This is done by using interrupts on the board. The result is a code that is easier to read and to manage. Later, you will find many methods that start with on. For instance, on key down. They are those wrappers for hardware interrupts. Finally, in the loop method of a program, we can code the logic of the board. Let's take a look at the startup program as an example on how to develop logic on the main loop. This is the program that shows the logo on the screen and blinks some LEDs before switching to the main program. It is a sort of bootstrap to start the board gently. In this code, you can see how to show stuffs on the display, how to switch on and off a LED, and introduce the program switcher that handles the cycling through the programs, and it is used to navigate to other programs. As I already mentioned, the program is the place where the logic is developed. So the idea is that people can develop their own programs to run the board in their preferred way. This could be done by editing the already present programs or creating a new one. The startup program class is a derived class from the base class program. If you take a look at the base class header file, you will find all the available methods that can be overridden. Now I guess you can get the picture. Overriding those methods with custom logic lets you do whatever you imagine without paying too much attention on the hardware part. You can do things on the initialization part or on the loop part. You can do things when a button is pressed or when an encoder is turned. You can use a MIDI controller to control the board. Let's take a look at the code of a very easy tutorial to draw some strings on the display and to turn the LEDs on and off based on a button pressed. Here you can see an empty initialization setup, the code of the loop, and the event handler of a key pressed. As the Microcosmos is developed over a Teensy board, the audio development can be done by the Teensy audio library. Its website says, a toolkit for building streaming audio project featuring polyphonic playback, recording, synthesis, analysis, effects, filtering, mixing, multiple simultaneous inputs and outputs, and a flexible internal signal routing. When I started working on this project, it was more than welcome having a visual tool to develop an audio DSP on a bare metal microprocessor. In a short amount of time, I was able to prototype different types of musical instruments. The integration with Microcosmos was very easy, and everything could be done in a single program. Here is the implementation of a simple program to demonstrate the audio capabilities of the audio library, integrated in the Microcosmos framework.
This is the audio system design tool for the Teensy audio library. Here you can design the audio signal path of the board. Here is a very basic path. An oscillator goes to a multimode filter that is connected with the three output, low pass, high pass and band pass, to a mixer that finally goes to the stereo audio out of the board. If you press export, you can copy the code to use in the project. Then you can paste it on the program of the project. I removed the include part as it is already present on the header file. The setup method does the initial setup of the audio objects, initializes the oscillator waveform and pitch, filter cutoff and resonance, and the mixer volume of the channels. Then set the encoders to default values to control the audio params, as they will control pitch, cutoff and volume. On the loop method, we can update the display to show the values of the encoders. This is done by the draw param line. The first parameter is the line number. The second is the display string. And the third is the value read from the encoder. The last part is the handler of the encoder's interrupts, the on-encoder change, where the first encoder at index 0 controls the oscillator's pitch, the second encoder controls the filter cutoff, and the third the output volume. And that's it.
The idea of developing a drone synth in less than 100 lines of code was very cool. But as soon as we started to go more deeply in designing the firmware, we found some limitation of working in this way. First of all, it was impossible to generalize parameters sent to object, because the code must know the object and the parameters we are about to change. So we looked for a solution to overcome this problem and generalize the way to send parameters to the audio DSP code. Our first attempt was to wrap audio object inside a generic container, but it required a lot of complex code. Also, it required a lot of documentation to make it usable by non-programmer people, so basically it was not feasible. Then we found out that Faust made an exporter for the Teensy audio library, exposing an object with the very convenient method setParamValue, and then we start a new version of the Microcosmos using Faust. On the Microcosmos, there is a special program called Microcosmos Faust program. It is a generic way to manage Faust scripts exported for the Teensy board. The principle is straightforward. Create the script with the Faust editor or a similar tool. Export the script to C++ code for the Teensy and replace the old one. Map the controls onboard and MIDI USB to the parameters of the script with a configuration file. Compile and upload the new firmware on the board. 4 steps to implement an audio prototype, almost without touching the C++ code, dealing only with the Faust script and testing it on a computer before running it on board.
Let's start importing a Faust script on the Faust web editor. The first part of this script contains some constants to make it more easy to edit. Microcosmos send parameters in the range from 0 to 127 to be compatible with MIDI control changes. The default params are always in this range, while the definition of low and high values depends on the various parameters. For instance, cutoff low and cutoff high are in the filter range in Hz, while the cutoff default is in the range 0 to 127. The two helpers here are the functions to map the values from the control change range to the real value. Then there is the UI part. All the sliders are put inside an horizontal group and mapped to the real values. Last part is the actual DSP code. Here we have an oscillator based on a square wave, then a low-pass filter and an envelope. Now we can test the script and check how it sounds. Now we can export the script for the Teensy. Just select Teensy from the drop-down. Click Export and download the code in the Faust project folder. Here we can remove the old folder and unzip the new one. Last thing to do is to update the Microcosmos config, where there is a mapping between controls and the Faust. Each item of the menu params is made up of 7 parameters. The ID of the control, the page of the display where it is placed. Every page can show up to 4 controls. The Faust param name, the displayed name, the default value, the MIDI control change, the locked status that is not used anymore. After setting the menu params, we're done and ready to compile and send to the board. We can do that with the Teensy software and pressing the upload button.
We've reached the end of the presentation of the Microcosmos. The original idea was to make a workshop, but of course the international health condition did not allow us to do that. So now you have a basic knowledge of the project and how it is designed. There are a lot of features we want to add to this board, and we hope we will receive feedback from you about improvements and new ideas. So thank you for watching, and thanks to the Faust International Conference for hosting us. You can find all the information on Microcosmos and other projects on www.faselunare.com. So long and stay safe. See you next time. Ciao!